Hi everyone, this is Sridhar Chintala, Assistant Professor of Physics, ABV Government Degree College, Janagam. So far we are making video lectures on the statistical mechanics, where it is from the BSc Physics second semester, Thermal Physics, and the unit is the fourth one, the statistical mechanics. So prior to this video lecture, we discussed the basics of the statistical mechanics and the one of the statistics, the classical statistics, Maxwell-Boltzmann statistics was already discussed in the last video. And in the present video lecture, I'm going to cover the Bose-Einstein statistics. So in the Bose-Einstein statistics, first of all, we define what is the system of Bose-Einstein statistics and what are the conditions to be satisfied by a system of Bose-Einstein, which is satisfied by Bose-Einstein statistics, and the applications of Bose-Einstein statistics. So this is my presentation. So Bose-Einstein statistics. And this is from BSc Physics. The paper title is Thermal Physics in the second semester, and which is in the fourth unit named as the Statistical Mechanics. So this is the complete picture which gives about the statistical mechanics, where the statistical mechanics is nothing but combining the statistics with the mechanics. The mechanics of the molecules of a gas, and it is linked with the statistics. The statistics is nothing but number. Since we are dealing with a gas, it consisting of almost 10 to the power of 23 molecules per unit volume. So as the number is more, we are dealing with the statistics, and we are trying to define the motion of the gas. So it is mechanics. So statistics and mechanics are combinedly, we are calling it as the statistical mechanics. And in the statistical mechanics, we are having two branches named as classical statistics and quantum statistics. So based on the treating of the number of molecules, so the classification as classical statistics and quantum statistics. So how we are treating the particles or the molecules of a gas. So the molecules of a gas are independent, similar, and distinguishable. Then it comes under the classical statistics. The particles are indistinguishable, and that comes under the quantum statistics. So as far as the statistical classical statistics is concerned, there is no restriction on the symmetry, but whereas the quantum statistics is concerned, there is a restriction on the symmetry. So again, the quantum statistics is divided into two types of statistics. So here the classical statistics is obeyed by the particles which are obeying the Maxwell-Boltzmann statistics, whereas the molecules of the gas are identical and distinguishable. And if the particles are indistinguishable, we have to switch over to the quantum statistics. And in the quantum statistics, if the particles are the identical and indistinguishable, beside indistinguishable, if they having a spin quantum number or spin number as 0 or integral multiples of h cut, so they comes under Bose-Einstein statistics. So the particles which obey Bose-Einstein statistics are named as bosons, and the particles are the molecules which obey the Fermi-Dirac statistics are named as fermions. So the fermions will have the integral spin as the half integral multiple of h by 2 pi, where h is the Planck's constant. So this is the major classification of statistical mechanics into classical and quantum. And again, the quantum mechanics is uh, classified into two: the Bose-Einstein statistics and Fermi-Dirac statistics, based on the Pauli's exclusion principle, where you call the Fermi-Dirac the particles which obey Fermi-Dirac statistics are fermions. The fermions must obey Pauli's exclusion principle. So, as the fermions are obeying to the Pauli's exclusion principle, we are having two types of statistics in the quantum statistics class. So, this is classical and quantum statistics, classical or Maxwell-Boltzmann statistics, and quantum statistics. So what is the need of quantum statistics is that the some of the phenomena were unexplained by classical statistics. Example of those are the photoelectric effect and the specific heat at low temperatures and the black body radiation. So these are the phenomena which were uh, unable to explain using the classical statistics. So there is a need of the quantum statistics. Again, the quantum statistics is again divided into two: Bose-Einstein statistics and Fermi-Dirac statistics. So the particles are identical but indistinguishable. Particles of zero or integral spin, those are comes under Bose-Einstein statistics. And if the particles are indistinguishable and having a half integral spins, they comes under Fermi-Dirac statistics. So the examples of fermions are electrons, protons, neutrons, and the examples of bosons are photons, pi mesons, and helium-4 atom. So these are the different statistics. So in the last class, we already discussed about the Maxwell-Boltzmann statistics. So in which the particles are identical but distinguishable. And in the today's class, we are going to discuss about the Bose-Einstein distribution law. And in order to distribute, in order to discuss, or in order to derive an expression for the distribution law, we have to have the knowledge of the system, which comes under Bose-Einstein distribution law or Bose-Einstein statistics. So in Maxwell-Boltzmann statistics, the particles are distinguishable from each other. That means if two particles are interchange their positions or energy state, a new state is generated. So that in the classical mechanics or in the Maxwell-Boltzmann statistics, we can identify the particles from one another. So if two particles are interchange their positions, that gives out to be a new state, that results into a new state. So that is the classical particles are distinguishable. But whereas in the case of Bose-Einstein statistics, the particles are indistinguishable. That means the interchange of two particles never gives to a new state or never result into a new state. So the particles in the Bose-Einstein statistics are indistinguishable, and the complete set of eigenfunctions for such a system are symmetric under an interchange of any pair of particle coordinates. So if you interchange any two pair of particles, it will be symmetric. And the statistic is applicable to particles which are having integral spins. So it is multiple of h by 2 pi, 0, 1, 2, 3, and so on and so forth. That means it is having integral spins. So the Bose-Einstein statistics is applicable to the particles which are having integral spins. So in order to derive the Bose-Einstein distribution law, let us consider a system of n independent identical particles. Unlike in Boltzmann MB statistics, the levels in Bose-Einstein system are discrete. Whereas in the case of Maxwell-Boltzmann statistics, we consider the energy levels as a continuum. So there we divided that spectrum of the system into groups. So that means the energy levels in the case of MB statistics are continuum, whereas in the case of Bose-Einstein distribution or Bose-Einstein statistics, the energy levels of the system are discrete. So each level can be occupied by any number of particles. There is no restriction on the number of particles which can occupy a given level. And the conditions in the Bose-Einstein statistics are the particles are indistinguishable from each other, so that there is no distinction between the different ways in which Ni particles can be chosen. For example, if we have 10 particles, so in order to choose the particle 1, so we can choose any particle, that means 1 to 10. So there is no particle labeled as 1. So we can name any particle as 1. So that means, so there is no difference or there is no distinction between in different ways in which Ni particles can be chosen. That is the meaning of the particles, the indistinguishability of particles. And each cell or sublevel of ith quantum state may contain any number of particles from 0 to n. So 0, 1, 2, 3 and so on and so forth up to Ni identical particles. It may contain 0 particles or it may contain Ni particles. Total particles may be occupied in one level, or it may be empty. So the sum of energies of all the particles in different groups taken together constitutes the total energy of the system, like in Maxwell-Boltzmann statistics also. The sum of energies of all the particles in different groups taken together constitutes the total energy of the system. And in this case, we have to assign Ni indistinguishable particles to Gi distinguishable levels when there is no restriction on the number of particles that can occupy one level. So in the case of Bose-Einstein statistics, we are having Ni indistinguishable particles, but there are Gi levels which are distinguishable by their energy. So if G1 level is there, the energy is E1. If G2 is level is there, the energy is E2, and so on and so forth. So that means we have to assign Ni indistinguishable particles to Gi distinguishable particles, so Gi distinguishable levels, when there is no restriction on the number of particles that can occupy one level. And Ni particles can be distributed in Gi states by a number of ways. So how do we distribute these Ni particles in Gi states? So that will be given by a number of ways. And number of ways can be obtained as follows. So here we are considering the system. So in the figure 2, the particles are in subcell 1, subcells 1 in subcell 2, 2 in subcell 1. So 2 particles in subcell 1, 1 particle in subcell 2, and there are no particles in 3, and there are 4 particles in 4, and 1 in 5, and so on and so forth. So we are taking the example of a distribution. So since there is no restriction on the number of particles, a cell may be empty, may even contain all the Ni particles. So as there is no restriction, we may have total Ni particles in the first cell, or the first cell may be empty. So the Gi subcells are constituted by Gi minus 1 partitions, which are represented by Gi minus 1 black balls. So these are the partitions. So in order to have Gi levels cells, there are Gi minus 1 partitions. So for example, if a room is there, if we put one partition, that will be divided into 2. And if we put 2 partitions, that will be divided into 3. So that means if you put n number of partitions, the rooms will be n plus 1. If you put n minus 1 partitions, the rooms will be n. So the same manner, the Gi subcells are constituted by Gi minus 1 partitions, which are represented by Gi minus 1 black balls in the figure. And the balls are labeled irrespective of their color with numbers 1, 2, 3, n plus Gi minus 1. So here there are Gi minus 1 partitions and Ni particles. So we may choose any particle or any level. So that means the permutations, the number of permutations possible are given by n1 plus gi minus 1 factorial. n1 is the number of particles and gi minus 1 are the number of partitions. So we may choose any ball, either black or white. So irrespective of their color, if we give numbers 1, 2, 3 and so on forth up to ni plus gi minus 1, the number of permutations are ni plus gi minus 1 and the number of balls, and the number of permutations are ni plus gi minus 1 factorial. So for each distinct distribution, there are ni factorial permutations of the white balls among themselves and gi minus 1 factorial permutations for black balls among themselves. So if you consider the black and white balls as a whole, the number of permutations are ni plus gi minus 1 factorial, and within the ni balls, if you want to choose one ball, the permutations are ni factorial, and within the gi minus 1 sub levels, if you want to choose one level, the permutations are gi minus 1 factorial. So that means we have to divide the total number of permutations by the permutations of white balls among themselves and the permutations of black balls among themselves, and that gives the probability of a particle to find in a given level. So these permutations do not give rise to any new distribution or change in the distribution of figure. So 2 particles in subcell 1, 1 particle 1 in subcell 2, 0 in subcell 3 and 4 in subcell 4 and 1 in subcell 5, etc. So, so we have ni plus gi minus 1 factorial, the total number of permutations, and among the total number of permutations, if you want to choose the white balls, there are ni 1 factorial, ni factorial, and if you want to choose the black balls, which are the what are called the partitions, so gi minus 1 factorial. So these permutations do not give rise to any new distributions. So that is the reason. Therefore, in counting, these permutations have to be eliminated, and therefore the number of distinct distributions of the particles for a state of energy EI as ni plus gi minus 1 factorial by ni factorial into gi minus 1 factorial. So this is the number of ways in which we can distribute the white balls among all the gi sub levels. Similar expressions will be for the various other quantum states. Therefore, the total number of ways in which n1 particles can be assigned to the level with energy E1 and n2 to E2 and so on and so forth is given by the product of such expressions as given below. So this is for the n1 level, and this is for the n2 level, and this is for the nith level. So first level, second level and ith level. So the total probability is given by the product of all these permutations. So W is equals to Ni plus N1 plus G1 minus 1 factorial divided by N1 factorial into G1 minus 1 factorial and N2 plus G2 minus 1 factorial by N2 factorial into G2 minus 1 factorial, and so on and so forth. If you write for ith level, this is ni plus gi minus 1 factorial by ni factorial into gi minus 1 factorial. And if you write this product as this one, pi ni plus gi minus 1 factorial by ni factorial into gi minus 1 factorial, where I runs from 1 to en. So that gives the probability of distributing ni white balls in gi minus 1 partitions or gi sub cells. with energies E1, E2, E3 and so on so forth. So the probability to become maximum, we have to have the variation in the probability, logarithm of the probability is equals to 0. For the maximum probability, we have delta log W maximum, delta log W maximum is equals to summation delta Ni log Ni plus Gi plus delta Ni minus delta Ni into log Ni minus delta Ni is equals to 0. Actually, we have W is equals to Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. So, where is that? Right. Applying logarithm on both sides, we have log W is equals to, this is log Ni plus Gi minus 1 factorial minus log Ni factorial plus log Gi minus 1 factorial. By using the Stirling approximation, the Stirling approximation is ln log of n factorial is equals to n into log n minus en. So this is the Stirling approximation. So we use this Stirling approximation in expanding this. So from that we have this one as the ln, this is log Ni plus Gi minus 1 factorial will be written as, I will erase this. So this will become Ni plus Gi minus 1 into log Ni plus Gi minus 1 minus Ni plus Gi minus 1 minus 1 total bracket. So when compared to the Ni number of particles and Gi subcells, so we ignore, in respect of Ni plus Gi, we ignore this minus 1, and this will become the equation as so the equation as we have Ni plus Gi into log Ni plus Gi minus Ni plus Gi. We have, for this expression, we have this. Similarly, we have for n factorial log of n factorial. So log of n factorial is also Ni log Ni minus Ni. Okay. So this Ni and this Ni will be cancelled. For Gi also we have this one. So Gi cancelled. So we are left with so after simplification, we are left with the before taking the differentiation, we are having log W is equals to Ni plus Gi into log Ni plus Gi minus log Ni minus, so we have Ni log Ni and Gi log Gi. We have this expression before taking the differentiation. So for the maximum probability, the delta n omega maximum will be equal to 0. So when you are taking the differentiation, this term will leads to 0 since these are the number of sub levels. So this is constant, so this goes to 0. So we left with these two terms, and in these two terms we have Ni and log Ni plus Gi and Ni log Ni. So there are 4 parts we have in total. So this is Ni plus Gi into 1 by Ni plus Gi into delta Ni. So next one is log Ni plus Gi into delta Ni. And this is Ni into 1 by Ni, and this is log Ni into delta Ni. So the simplification will be given in the above equation. So after all simplifications, we have delta log omega, so W maximum is equals to summation delta Ni into log Ni plus Gi plus delta Ni minus delta Ni into ln log Ni minus delta Ni. So this is plus delta Ni, this is minus delta Ni, will be cancelled, and we have summation I log Ni plus Gi minus log Ni into delta Ni is equals to 0. And this represents the maximum probability. So hence for the W represents a maximum, so this will be equal to 0. And the system also satisfies the following conditions: that the total number of particles is constant and the total energy of the particles or the system is constant. So we are including these two conditions in the above equations by multiplying with some constants. So this is summation delta Ni is equals to 0, and this is summation Ei delta Ni is equals to 0. So this represents the total number of particles is constant, and this represents the total number of total energy of the system is constant. And we are incorporating these two conditions in the above equation, and our equation is 6.29 will be changed as so multiplying 6.30 by minus alpha and 6.31 by minus beta and adding to 6.29 will get summation log Ni plus Gi minus log Ni minus alpha minus beta Ei into delta Ni is equals to 0, and the variations delta Ni are independent of each other, hence we get this term goes to 0. As we are having A into B is equal to 0, B can never be equal to 0, so A is equal to 0, that is log Ni plus Gi by Ni minus alpha minus beta Ei is equals to 0. So this gives the condition as, so this is Ni plus Gi divided by Ni is equals to e power minus lambda. So when it is going that side, it will be equal to plus lambda plus beta Ei, and this is equal to Ni plus Gi by Ni. And if you write for Ni, so this will be equal to Ni into e power alpha plus beta ei minus Ni is equals to Gi. So if you take the Ni as common, so Ni is equal to Gi by e power alpha plus beta I minus 1. So this is the resultant equation. So that gives the distribution of Ni particles in Gi sublevels, taking the permutations and combinations into consideration. So Ni is equal to Gi by e power alpha into e power ei by kt, where beta is equals to 1 by kt minus 1. And this is known as the Bose-Einstein distribution law. This represents the most probable distribution of the particles among various energy levels for a system obeying BE statistics. And next we have the applications of, we have to discuss the distribution graphically. So taking Ni by Gi on y-axis and Ei on x-axis, that is the distribution Ni by Gi as a function of Ei. So that gives out to be graphs like this. So this is the graph which represents the high temperature range, and this is the graph which represents the low temperature range. So the distribution of particles for different energy levels is as shown in figure for low and high temperatures, and then the B distribution law has more emphasis on the low energy levels. So then the applications of Bose-Einstein statistics. So one of the applications of Bose-Einstein statistics is to the photon, that is the Planck's distribution law. The application of Bose-Einstein distribution to derive the Planck's radiation formula for the photons. So Planck's radiation formula, as far as the photon is concerned, it is a boson having integral spin as equals to 0 and integral spin is equals to 1 and the rest mass is equals to 0. So we shall study the applications of Bose-Einstein distribution to photons and obtain Planck's radiation formula. So in order to derive the Planck's radiation formula, consider a box containing the electromagnetic radiation, that is the photons, at a temperature capital T. These photons would be absorbed and re-emitted by the container walls. So as the light is entering, as the radiation is entering inside a box, and that undergoes reflections, and in the reflection, the photons are absorbed by the walls of the container and re-emitted. So in this process, under thermal equilibrium, the energy distribution can be determined by the Bose-Einstein statistics. So in order to derive the formula, we have to consider some important properties of the photons. They are particles of zero rest mass, and they are indistinguishable from one another since they are obeying the quantum mechanics or quantum statistics, and they have spin quantum number is equals to 1. So there is, however, there is an important difference between the photons and the other bosons, namely photon number is not conserved. This is because the walls can absorb a photon of energy E and emit several photons of energy E1, E2 and E3 and so on and so forth, such that the total energy E is equals to E1 plus E2 plus E3 and so on and so forth. So thus we have only the energy restriction, the conservation of energy, and there is no restriction on the photon number, the non-conservation of photon number. So in this case, delta Ni is not equal to 0. Generally, we consider in the starting of Bose-Einstein statistics as the total number of particles is constant. But in the case of photons, the total number of particles is not equal to constant, and it is, if you consider the change in the number of particles, that gives to be non-zero value. So that's in this case, delta Ni, summation delta Ni is not equal to 0. So that means we must drop the auxiliary condition of delta Ni is equals to 0, and therefore the undetermined multiplier alpha is equals to 0, and we have the Bose-Einstein distribution formula as f of e is equals to 1 by e power alpha into e power e by kt minus 1, and this alpha in this expression goes to 0 since the number of photons is not conserved in the case of photons. So we have f of e is equal to 1 by e power capital E by kt minus 1, and this alpha goes to 0. So since alpha is equals to 0, the Bose-Einstein distribution function for photons becomes f of nu is equals to 1 by h nu by e power h nu by kt minus 1, where e is equals to h nu, and the number of independent standing waves per unit volume in the frequency interval from nu to nu plus d nu is given by g of nu into d nu is equals to 8 pi nu square by c cube into d nu. So this is we derived from the number of density states. So the energy density of radiation in the frequency range nu to nu plus d nu is given by E nu d nu is equals to h nu into g nu of f of nu into d nu. This is the energy of each photon, and this is the density states, and this is the what is called the distribution function. So the total density of radiation in the frequency range nu and nu plus d nu is given by 8 pi h by c cube into nu cube d nu into e power, so divided by e power h nu by kt minus 1. And this is the Planck's radiation formula, which is we derived in the first quantum theory of radiation, the third chapter. So this agrees with the Planck's formula and with the experimental curves. So this is the one of the applications of Bose-Einstein statistics to photons to derive the Planck's radiation formula. So far in this video lecture, we discussed about what is called the statistical mechanics, the major classifications, and Bose-Einstein statistics and the Fermi-Dirac statistics, and what is the system of under Bose-Einstein under consideration for the Bose-Einstein statistics, and what are the conditions to be satisfied of a system under Bose-Einstein statistics, and what is the distribution function, and how the number of particles are distributed in the given subcells by obeying the what is called the conditions in the B statistics, and the application of Bose-Einstein statistics to photon in order to derive the Planck's radiation formula. So this is about the present lecture. So thank you for your patient listening, and we'll discuss the next, that is the Fermi-Dirac statistics and the applications of Fermi-Dirac statistics in the upcoming video lecture. And thank you for your patient listening.